Hey there, welcome back to Calculus. In this section 3.6, we're going to take a look at how to differentiate logarithm functions. Logarithms, you recall, are the inverses of exponential functions. So you can take a look at our objectives there. You'll notice that on the Canvas page, there's one more objective, something called logarithmic differentiation. I'm going to cut that into a separate video so that these stay a little shorter and more focused. So our purpose in this video here is to, well, the main purpose is to derive the derivative of the natural logarithm function. It's going to be the most prominent base that we're going to use, so we're going to start with it. And then I'm really just going to kind of allude to that the same method can be used to derive the derivative of arbitrary logarithmic functions. So we'll state that result. We'll look at a couple of examples and circle back through some ideas. I think we're going to find a tangent line and look at some graphs, always thinking about derivatives as slopes and rates of change. And that'll wrap us up. Okay, so let's get started. I want to start with a little bit of review about exponential and logarithmic functions. So let me just bring this into the screen here. I'm not going to review this in terms of general bases, but if you want, that red curve really is kind of the scaled version of any exponential function, b to the x, where b is greater than 1 anyway. And that logarithm curve down there would be the corresponding log base b, but I'm going to stick to the base e here, the natural logarithm base. So I've got drawn in red there e to the x. And I'm highlighting kind of one of its features. Things that I want you to know about the exponential function, if you like, that its domain is all real numbers. The exponential function is defined for every number on the x-axis. Its range is only positive numbers. We've talked about this before in previous videos. The y-intercept of any exponential function is always y equals 1. Anything to the 0 power is 1. And if the base is bigger than 1, like e here, then the exponential function increases, and it increases actually faster than any polynomial function as x goes to infinity. Its logarithm, in this case the natural logarithm, because I'm talking about the inverse of the natural exponential function, well, it's the inverse of it. So e to the x and log of x. I should pronounce this natural log of x, but I'm just going to say log of x. It's written, and so if there's any ambiguity, I'll try to clear it up. But if you hear me saying log, I really mean natural log if I'm writing ln. They're inverses of each other in the following sense, that if you take an x value and you plug it into the natural logarithm function, it's the first process, and then you take that and plug it into the exponential function, the second process, you get the original x value back. Yeah, so these processes, natural log and e, they undo each other. That's what inverse functions mean. And they undo each other in both ways. If you take your x and you first exponentiate it, so you let the exponential process go first, you let it be inside in the chain rule language, and then you take the log of that, you're going to get your x back. Okay, that's what inverse functions do. They compose to give the identity function. If you write that in terms of equations, if you have some exponential equation, y is equal to e to the x, well, taking the natural log of both sides and remembering that the natural log of e to the x is x, the logarithmic form of that equation is just natural log of y is x. And conversely, a natural log equation y equals log x has an exponential form, e to the y is x. So you can always pass back and forth between the exponential and natural log or logarithmic forms of an equation by applying the inverse operation. All right, our goal here in this lecture is to compute the derivative of the natural log. That's what I want to do. I know how to differentiate e. Yeah, I know how to differentiate the inverse function. So we're going to use that same technique we were using in the previous section. I'm going to just use the fact that I know the derivative of the inverse together with implicit differentiation to derive this thing. All right, so let me scroll down a little bit and let's get started. I think I've just written the calculation out. So let me just narrate it for you. All right, so starting over here on the left-hand side, I'm writing that y is the natural log of x. I'm just reminding you here that that means that x is positive. The natural log's domain is only the positive numbers, the range of the exponential function. And so I'm going to just take that natural log equation and write it exponentially. If y is the natural log of x, then e to the y is x. Yeah, just exponentiate both sides. And now differentiate implicitly. Take the derivative with respect to x of both sides of that equation. So you get the derivative with respect to x of e to the y is equal to the derivative with respect to x of x. Well, on the left-hand side, because we're doing this as a function of x, we're differentiating with respect to x, that derivative is e to the y times dy dx. That's our inside function, its derivative. It's chain rule. Derivative of x is 1. Okay, then like any implicit differentiation problem, we solve this for dy dx. We can do that just by dividing by e to the y. So we get dy dx is 1 over e to the y, but e to the y in terms of x is just x. Yeah, so there's our differentiation formula. The derivative of the natural log function for positive x is the reciprocal function. Or if we summarize that in a nice box like this, the derivative of the natural log of x is 1 over x. Okay, it's a new fact. And I have to think about this. It's not quite the end, but you now know how to differentiate polynomial functions, all the trig functions, exponential functions, logarithmic functions. So really the family of functions that I want you to be able to differentiate is nearly complete. These are going to be our sort of cast of characters, if you like, and as we move into chapter 4, which is all about applications of all of this differential calculus to problems in science, chemistry, physics, engineering, biology, and so on. Geology, I should mention geology too. So that's what chapter 4 is all about. So these are the functions that we're going to be using there. All right, so I'm not going to go through the details. You can read it in your book. Your book actually does it first, but in the same way, because the natural law, or excuse me, the log base b of x is the inverse of the exponential function b to the x. In the same way, using implicit differentiation, you can derive that the derivative of the natural log, or sorry, the log base b of x for any base b is 1 over x times the natural log of b. Yeah. So maybe I should recall here that the natural log of e is 1, which is why this formula is so nice. You don't have to remember that extra factor down here. This, if you're differentiating with a base other than the base e, you need to remember that the derivative, the denominator, has this factor log base b in it. All right, I'm not saying that we're never going to use logarithms with bases other than e, but it will be rather infrequent. So in terms of like the important formula of what we're talking about here, well, I shouldn't call it important like the other one isn't important, but this one that I'm outlining in red we'll be using much more often. All right, so it's a fact, just like you've kind of already hopefully internalized the derivative of sine is cosine, the derivative of e to the x is e to the x. I want you to internalize that fact, that the derivative of the natural log is the reciprocal function. Cool. Let's do some examples. Let's do some examples. Here I've got a function f of x. It's the natural log of x to the 4th plus 1. Let's compute its derivative. All right, this is a chain rule problem because I've got inside the natural log, I've got this polynomial function x to the 4th plus 1. So to compute the derivative of that thing, we're going to need to use the chain rule. So if we start off the computation, the derivative is, well, it's the derivative of the outside function. The outside function here is the logarithm. The derivative of logarithm, if I tried to scroll back up to where we can still see it, we won't be able to write much, but it's the reciprocal function up there. So if I take the derivative of the outside function, it's 1 over, and I have to evaluate it at the same inside function. So the computation starts off 1 over x to the 4th plus 1, but then I need to multiply that by the derivative of x to the 4th plus 1 by the chain rule. That's the derivative of my inside function. So if I do that out, this 1 over x to the 4th plus 1 isn't doing anything. The derivative of x to the 4th plus 1 is 4x cubed. Yeah, and I can write that as a single fraction, certainly. I can write it as 4x cubed divided by x to the 4th plus 1. So there's our derivative of the natural log of x to the 4th plus 1. All right, that pattern is actually pervasive. Anytime you're differentiating a natural log function, you're always going to have 1 over what's inside of it times the derivative of what's inside of it. That's how the chain rule is always going to work. So the book actually summarizes that in these two formulas, one written in this variable u and one written in g of x. These two formulas don't say different things, they're just different notations. But in both cases, you have an inside function, u in this one, g of x over here. In our example that you can still see, u or g of x was equal to x to the 4th plus 1. And the derivative of the log of u, well, it's always 1 over u times du dx. Or the derivative of log of g of x is g prime of x over g of x. So look at that up here. Here's your g of x, x to the 4th plus 1, and there's its derivative, g prime, 4x cubed. So logarithms always have this pattern. Just like exponentials, the derivative of e to the g of x is e to the g of x times g prime. Well, the derivative of log of g of x is g prime over g. Important pattern to catch on to. All right, let's do some more. Let's do some more. The rest of this lecture is just some sort of skill and drill here. Let's see what I got. Let's leave those formulas right there. Here I want to compute the derivative of, pardon me, I forgot something. Let me fix this on the fly. More evidence that I don't know how to edit videos. I meant the derivative of the natural log of that fraction, not just the fraction. There, that's the example that I intended. Let's take the derivative with respect to x of the natural log of x plus 7 over the square root of 3x plus 5. Yeah, so what have I done? I've given you some elaborate g of x. G of x is this quotient, the square root, or x plus 7 over the square root of 3x plus 5. All right, so let's use the formula above. The derivative of that thing is, well, 1 over it. 1 over a fraction is just the reciprocal of the fraction. So I'm going to write that like this. 3x plus 5 in the numerator, square root rather, divided by x plus 7. So that's my 1 over u. It's this part, yeah, or my 1 over g of x. And then I need to multiply that by the derivative of that fraction. And I'm going to write that 3x plus 5 square root as a 1/2 power here, because I'm going to be differentiating it here in a second. So there's our pattern. Now let's scroll down so we have some room and see if we can't crank this thing out. So, and actually I'm going to left justify this a little bit more, so I'm guaranteed to have enough room. All right, so this first factor, the square root of 3x plus 5, is just coming along for the ride. I want to keep everything organized nicely. And now I'm focusing on the quotient rule pattern for that derivative. Yeah, so the quotient rule pattern is a big fraction bar, quotient rule. You square the denominator. Well, when you square the square root of 3x plus 5, you just get 3x plus 5. And then you have to write that denominator down. That's 3x plus 5 to the 1/2, or square root if you like, and then we have to multiply that by the derivative of the numerator. Let me just write the quotient rule pattern, and then I think we have enough room to do the simplification in the next line. So then you subtract the numerator undifferentiated times the derivative of the denominator. So that's our 3x plus 5 to the 1/2. Got to take its derivative. All right, so I didn't do any of the details. I just wrote the quotient rule pattern out. But my advice, especially for you as you are a beginner at this business, if you're patient and write out steps like that, like I just did, you'll minimize your errors. And moreover, if you do make an error, by having many steps written out, it's much easier to go back and see where the error happened. Yeah, if I got the answer wrong, if I get down to the bottom of this calculation and I look in Slater and my answer is not the same as Slater's, then I can just go back up here and start line by line and go, well, what did I do? It was the 1 over times the derivative. Okay, here's the quotient rule. Did I get that right? I can check all my signs and so on. So leaving yourself lots of breadcrumb trails, lots of little steps. It helps improve your accuracy and also helps you find your errors if you make one. Okay, but enough sermon here. Let's just simplify this thing a little bit more. So I've got 3x plus 5 to the 1/2. Now I'm taking the derivative. I'll just show you where I'm looking. The derivative of x plus 7 is 1. X plus 7, derivative of this square root term, that's also a chain rule problem, yeah? Because I'm taking the 1/2 power of 3x plus 5. So I'm just going to do this on the fly here so I don't run out of room. So that's 1/2 3x plus 5 to the minus 1/2 times the derivative of 3x plus 5, which I'm just going to write as 3. All right, so this problem is quite involved, but notice at any given moment, I never have to be thinking about too much. Divided by 3x plus 5. Okay, the calculus is over. All the derivatives have been taken. What could I do to simplify this thing a little bit? I don't really think I'm going to do all that much. I could factor out a 3x plus 5 to the 1/2. Maybe I'm going to do it just to illustrate something that'll be handy for us in the future. But I've got a 3x plus 5 to the 1/2 here, and I've got a 3x plus 5 to the minus 1/2 over there. Well, you can factor 3x plus 5 out of that, or to the to the minus 1/2. You can pull out the smaller exponent. So I'm going to factor out 3x plus 5 to the minus 1/2 out of this expression. All right, so this is going to be the last little bit of algebra I'm going to do. This factor out here, square root of 3x plus 5 over x plus 7 is not doing anything. And then I'm going to pull this 3x plus 5 to the minus 1/2 out of my numerator. Put that denominator down there. And then what would be left? I think the trickiest part probably is this thing. So what do you get when you factor 3x plus 5 to the minus 1/2 out of 3x plus 5 to the plus 1/2? Well, you have to subtract the exponents. So you have to take this 1/2 and subtract minus 1/2. 1/2 minus a minus half is 1. So maybe you can come to an office hour and ask me about this if it's not clear. But when I factor that out, I'm going to have 3x plus 5 to the first power. Okay, and then down here, the rest of this stuff, I've just got 3/2 times x plus 7, and I'm out of room and also losing interest in this algebraic simplification, so I'm just going to leave it like that. There's certainly some more we could do. There's some more we could do. In particular, I'm almost unable to resist the temptation of taking this 3x plus 5 to the 1/2 and the minus 1/2. They cancel. So you get 1 over x plus 7 times this thing, and then you can continue to massage it from there. But I'm out of room, so I'm just going to leave that to you. All right. Maybe you could post a simplified version of this answer on a discussion forum, and we can all congratulate you. That would be kind of a cool thing to see. All right. So let's continue on here. I think I've got a couple more examples. I don't want this video to get too long. You know that I like the habit of circling back through old ideas. So hopefully we're getting comfortable with finding equations of lines, and you know what I mean by a tangent line. You need the derivative. So we need the derivative to plug in the value x equals 1 to get the slope that we need. So differentiating this thing, it's product rule problem. Yeah, it's x squared times log x. So let's start by computing that derivative in terms of x. So at this time, I think I'm just going to write the product rule as I go. So hopefully the product rule pattern is getting familiar to you. But how does it work? You take the first factor undifferentiated and you multiply it by the derivative of the second factor. So that's the 1 over x is the derivative of log x. And then you have to take the other way around. Take the derivative of x squared and multiply that by the second factor undifferentiated. Right? So if we simplify that just a teeny little bit, what do we get? We get x plus 2x log x. So if we want to know the derivative when x is 1, we have to plug 1 into that. The natural log of 1 is 0. Yeah? Natural log of 1 is 0 because e to the 0 is 1. So the slope that we end up getting is just 1 plus 0, or 1. All right, so f prime of 1 is 1. We have our point is 1 comma 0, so our line, I'm going to use the point slope form. Y minus 0 is the slope times x minus 1. Or that simplifies super nicely into y is equal to x minus 1. So there's our tangent line. And I don't want this video to be too long, but let's switch over to Desmos real quick. I've got a Desmos window waiting for us. Let's plot this function and that tangent line to see if we have something that looks reasonable. All right, so how do I plot the natural log in Desmos? Well, I want x squared and then times it. You can come down here and find it in this thing if you want. It's over here in functions. Which one? I think it's in miscellaneous. Right there, there's the natural log function. You could also just type ln. I personally think it's much easier just to type. So I'm just going to type it ln of x. It knows what I mean. So there's the picture, and notice that it's only plotting it for x positive because the natural log function only has the domain x greater than 0. All right, if you want me to zoom in or out, I can do that, but I'm just going to leave it like that. And now let me type our tangent line. We said our tangent line was x minus 1. All right, so the question we're asking ourselves is, do we think we got the answer right? You could zoom in a little bit on that if you wanted to look at more detail. It looks to me like that blue line is touching the red curve at the point 1, 0, and locally that's the only point. It's got the right direction. All right. So I'm always encouraging you to look at these Desmos graphs. You can, in some sense, never get a tangent line wrong if you're willing to fix it in the case that something looks wrong with your picture. All right. So here we're coming back. I hope, trying to talk my laptop into bringing my iPad screen back. There, you got it. Okay, cool. All right, let's keep going. Getting near the end here. This is just kind of a fact to expand things. I just said the domain of the natural log function is x greater than 0. If you want to expand that domain a little bit, one way to do that would be to take the natural log of not x, but the absolute value of x, right? The absolute value of x is always positive. So as long as x isn't 0, we can take the natural log of its absolute value. If x is positive, we're just taking the natural log of x. And if x is a negative number, if x is less than 0, the absolute value of it is its opposite. So there's a formula for this thing piecewise, if you like. We already know how to take the derivative of natural log for positive x, so I'm just going to focus on the negative one down here, and I'm just going to use the chain rule. So what am I saying? I'm saying the derivative of the natural log of negative x, the opposite of x, well, it's 1 over the opposite of x times the derivative of the opposite of x, and that's -1. And 1 over negative x times -1 is 1 over x. So it actually doesn't matter if x is positive or negative. The derivative of natural log of x is also the reciprocal function. So this is sort of a more general result. It expands the domain. This formula is valid as long as x isn't 0, right? So x doesn't have to be strictly greater than 0. It can be negative. It just can't equal 0. So we're going to end this just by kind of enjoying that graphically. I took a picture from your book and modified, because in your book it was like example 6. In our lecture it was example 4. So I'm just making that little modification for you here. And what's it showing us? Well, it's showing us a graph of the natural log of x, the absolute value of it. So hopefully this side looks familiar. That is certainly what the natural log looks like. And by putting the absolute value around it, well, we just get this sort of symmetric piece. There's no y-intercept, there's no graph, there's no point on the y-axis, but that blue curve is the natural log of absolute value of x. And the red curve is the graph of 1 over x. And you can see 1 over x is negative if x is negative. The y values over here are all less than 0. 1 over x is positive if x is positive. So you can kind of stop the video and make sure that you think that the slopes are represented accurately on that pink curve. Like watch, as x goes to 0 from the right, it looks to me like the tangent line slopes are becoming very big and positive. Well, that's consistent. The y-coordinates on this graph are heading up to infinity. I personally think this is interesting. I don't know if you know this, but it is a fact that the natural log function doesn't have a horizontal asymptote. The natural log function will grow without bound. As x goes to infinity, the natural log function will just keep getting bigger and bigger and bigger, but it does so very slowly. So it keeps growing, but it grows very slowly. In fact, so slowly that its tangent slopes are approaching 0. So there is no horizontal asymptote. This graph is never flattening off in the sense that it's approaching some y value that's fixed. It'll pass any y value. You give me a number on the y-axis, and eventually the natural log function's output will exceed that y value. But at the same time, as you look further and further out, the slope is approaching 0. So that's kind of an interesting phenomenon about the growth of this function. It grows without bound, but it kind of does it as slowly as possible in some sense. Okay, so in the next video lecture, I'm going to show you a cool algebraic technique called logarithmic differentiation, but I think it's better to cut it off and put it in a separate video so you can focus a little more. So thanks for listening.